Good morning, everyone. Hope you have a wonderful day today. We're going to go over section 3.6, which is over polynomials inequality. So up to this point, we've been solving for zeros. So what does that mean? Anytime that we solve for zero, we set the function equal to 0 and basically find out where the graph crosses the x-axis. So for example, if I have a function that looks something like this, then what I'm trying to find is basically all these points right here. We call those zeros, or commonly known as x-intercept. Now we're going to look at inequalities, which means that we're going to look at where the function is above the x-axis or when the function is below the x-axis. Now, if you have equality in here, you would include the zeros, okay? All right, so here's our procedure. We're going to express the inequality in the form of less than 0 or greater than 0, where f is our polynomial function. And we're going to solve the equation for f of x equals to 0, okay? So this is what we've been doing up to this point, just solving for it equal to 0. So the real solution are the boundary points. So these are now called boundary points. So now we don't have another name for it. It all means the same thing. Now I'm going to show you why it's called boundary points. So the reason why it's called boundary point is that these are the endpoints of where the graph is above or below the x-axis. As you can see here, these 2 points right here are the boundary points for when f of x is above the x-axis. And so also this portion right here. So the green portion, I'm going to underline here, is the portion of the graph that is above the x-axis. Okay, I'm going to use red for when the function is equal to the x-axis, and then we'll use blue to denote when f of x is below the x-axis. So this portion right here. Okay, so you can see there's 3 different type of solution. You can either have it equal to 0, where you have the boundary point. You can have it above the x-axis, where you have the green portion, and you have the below x-axis, or the blue portion. Now you can combine either one of these here with the equality. So that means that you can just include the boundary points. Okay, so there's different ways that we can do that too. All right, so once we solve for it, once we find the boundary points, we're going to divide our number line using these boundary points. So as you can see here, this graph goes to negative infinity and positive infinity. So we're going to divide up the number line into 1, 2, 3, 4 different intervals. Now we have 3 boundary points, so therefore we're going to have 1 more intervals. Okay, so it's always going to be the case. If you have 1 0, you're going to have 2 intervals. If you have 2 zeros, you have 3 intervals, and so forth. So the number of intervals is almost always going to be n minus 1, where n is the number of boundary points. Now, it's not always the case. I'll show you this here. Let's say I have something like this. I think that's still true, right? Yeah, it's still true. Okay, so I divided. I have 2 boundary points. I have 1, 2, 3 intervals. Yep, so this is always true here. Okay, so after that, we're going to choose a representative number called a test value. So you just pick that number anywhere inside each one of these intervals, and we're going to test it. And we're going to see if it's positive or negative. So if it's positive, it's going to be above the x-axis. If it's negative, it's going to be below the x-axis. And that means that all of the points in that interval is going to be below or above the x-axis. All right, so let's do an example here so we can go through each step. All right, so now we need to solve for this by setting it equal to 0. So here we need to move this 3 to the other side and set it equals to 0. So that is our step 1. Okay, step 2, we're going to solve for it. So we're going to do that by factoring. So that means that these are our boundary points. Okay. Step 3, we're going to locate these boundary points on a number line, thereby dividing number lines into intervals. So we're going to draw a number line. -1 and 3. Okay, so now we divide it into 3 different intervals. So we have 2 boundary points, we divide it into 3 different intervals. Now we need to pick test values. So here we're going to choose one representation number called a test value. So step 4, I'm going to choose, let's see, -2 in this interval. I'm going to choose 0 in this interval. Always choose 0. It's the easiest one to plug in. And then I'm going to choose 4 in this interval. So now I'm going to try to evaluate these numbers of this function here. Okay, f of -2. So I'm going to use the factored form in order to plug in. Now, remember, I only care if the number that I'm getting is a positive or negative number. I don't care what the actual number is. So if I plug in -2 in here into the factored form, -2 minus 3, that is a negative number. I don't care what number it is, just care if it's the sign. Multiply with -2 plus 1, that's a negative number. So a negative times a negative is a positive number. So that means that this is going to be a positive value. So that means that all of the y value in this interval is going to be above the x-axis. Okay, let's look at 0. 0 is easy. I'm going to plug it into this form because this is much easier to plug in. So that goes to 0, that goes to 0. So I have a -3, so that's a negative number. All right, f of 4, I'm going to use the factored form, which is much easier. 4 minus 3, that's a positive number. 4 plus 1, that's a positive number. Positive times a positive is a positive. All right, so now let's look at what I want. So originally, I'm trying to solve for x squared minus 2x is greater than 3. If I bring this over here, I have x squared minus 2x minus 3 is greater than 0. So I'm trying to look for the portion of the graph that is above the x-axis, which means that it's positive. So I'm going to look for all of the positive portion of my interval. Here's one. Here's another one. And let's double check to see if you want the boundary points or not. Since you do not have equality here, you do not include the boundary points. So we leave out those boundary points by using parentheses instead of bracket. So that means that my solution in interval notation is from -infinity, because this arrow is pointing to the left, to -1. And I'm going to put a U for union from 3 to positive infinity. Okay, so now let's show you the graph of what this looks like. So this is just a simple parabola, x squared minus 2x minus 3. And we know that the zeros is at -1 and 3. And this is a parabola that opens upward. So you can see here, this portion of the graph is -infinity to -1. This portion of the graph is 3 to infinity. And you can see here that both of these intervals are above the x-axis. therefore satisfying our inequality that it needs to be greater than the x-axis. Okay, let's look at another example. Same thing here. We're going to set equal to 0 first. Okay, so we're going to set equal to 0. So I just bring this over here. Set it equal to 0 to find boundary points. Now we can factor this out. So my boundary points are, so BP for boundary points, x is equal to 0, 2, and that's it. We have a multiplicity of 2 here. So we only have 2 boundary points. Draw a number line, 0 and 2. Okay, so here we're going to see that we need to pick some numbers. So I'm pick -1, 1, and 3. And we're going to evaluate at these points. So I'm going to choose a, so notice here I'm going to rewrite this as x times x minus 2 square. Now, the thing about this square right here is always positive. So no matter what number I plug in here, it's always going to be positive. So I don't really care to evaluate this factor right here. So the only thing I'm going to look at is this x, because that's the only value that is going to determine the sign of the whole thing. So if I plug in -1 in here, I'll show you -1. -1 minus 2 is -3, but it's being square. So this part right here is always positive. This here is negative, so that's going to give me a negative when you multiply it. So over here, I'm going to get a negative. And then when I plug in 1, that's going to be positive. It's a positive 1 when you plug in here. 3, also positive. So now we want to know the portion of the graph that's less than or equal to 0. So that means that this time we're going to include the boundary points. Okay? So if inequality have equal, then you need to include boundary points. Okay, so now I want the portion that's less than 0, so I want to include this one right here, and don't forget to also include the boundary points, this one and this one. So this portion of the graph is -infinity to 0. I want to include the boundary points. Union with one single element here, so just 2. Okay, same thing. So we're going to solve for this here. So x is equals to 9, so x equals to plus or minus 3. Let's graph it. So we're going to pick -4. Always pick 0 if you can. Okay, so when I plug it into this inequality here, -4. So -4 squared, that's going to be 16 minus 9. That's a positive. Plug in a 0, that's a negative. Plug in a positive 4, that's a positive. So now I want it to be less than 0. So I want just this portion right here. There's no equality here in the inequality. So I do not want to include the endpoints. So I'm going to use an open circle instead of a closed circle. So my interval notation is from -3 to 3, not including the boundary points. All right, going. Okay, set it to one side. And then set it equals to 0. Factor out. found our boundary points. So we have 2 boundary points. Graph it. Pick a number in each one of these intervals. -1, 1, and 6. Now you can choose 7, 8, 9, 10, doesn't really matter, as long as inside this interval. Plug in -1. Now you can see here, in this portion, x is always being squared, so this is always positive. So I don't really care about this portion here. Now I'm going to plug in -1 into here. I'm going to get a negative number. I plug in 1 in here. I'm going to get a negative number. I plug 6 in here. I'm going to get a positive number. Now here we see that we want it to be greater than or equal to 0. So I want it to be positive, and I want it to be equal. So I need to include this number, and I also need to include this number. So I need to include 0 union from 5 to positive infinity. Okay, last one. Okay, so this time I have 4 intervals that I need to check. And I'm going to plug it in here. Okay, so f of -3. So that's going to make this number here negative. And then -3 squared is 9. 9 minus 4 is going to be positive. So this is negative. Okay. Plug in a -1. So I have a negative times -1 squared is 1. 1 minus 4 is a negative. So negative and a negative is a positive. And then f of 1 here, plug it in, I get a positive and a negative. So that's a negative. F of 3, positive, and a positive. It's a positive. Okay, so I'm also going to show you another way here. Now, we know that this is a cubic function, right? Now, you also know how to graph these. Well, this is cubic, x cubed minus 4x. So it's odd. Leading coefficient is positive. So odd and positive have an end behavior of down to the left and up to the right. And then you know that each one of these only have a multiplicity of 1. So it's going to go straight through it. So it's going to look something like this. Right? So you can also sketch your polynomial in order to determine this without doing this graph if you feel like this is faster. So right here, you can see that from -3 to -2, it is negative or below the x-axis. You can see here. From -2 to 0 is positive. It's above the graph. You can see here. Here is below the x-axis. Here is above, and we have everything we need. So I want it to be greater than or equal to 0. So I need to include all of my boundary points, and I only want the positive portion. So this one and this one here. So I want it from -2 to 0, union with 2 to positive infinity. So I want this portion and this portion right here, including the boundary points as well. All right, well, that's it. Next time we're going to go over chapter 1.6, and then we will be able to take our tests after we come back from spring break. All right, have a great spring break. Stay safe, and I'll see you next time.